Okay, so this is going to be the last workshop in the set, and we're going to sort of cumulatively kind of apply a lot of the stuff we've talked about in earlier sessions into actually building a neural network in TensorFlow. So the two sort of libraries you'll typically see mentioned when it comes to training neural networks are TensorFlow and PyTorch. I personally usually use PyTorch, but this notebook is in TensorFlow. I've linked a PyTorch demo as well in this notebook, although we'll be looking at TensorFlow primarily. The two of them are pretty comparable. I wouldn't say one is like explicitly better than another one. Out of the two, I would say they're just sort of different in syntax and in how you manipulate some of the matrices and tensors and whatnot. TensorFlow is a nice kind of thing called TensorBoard that's connected with it that lets you look at how models are like learning and stuff. But I mean, with PyTorch, you can basically get the same thing by just plugging it in with like a third-party kind of package as well. So they're pretty comparable. I think it's just at the end of the day, personal preference kind of thing. I'll probably also like briefly show some PyTorch syntax towards the end, just so y'all can get like a flavor of it, but it's not a huge difference. Very much just personal preference. Yeah, these are both Python. I believe these are both native to Python. So like they're written for Python. That's why typically a lot of people use Python for machine learning because it has such good like package support. So you have like TensorFlow, you have Keras, you have PyTorch, you have stuff like scikit-learn, which is a very useful kind of like thing for some of the simpler models, like what we talked about with like logarithmic regression or nearest neighbors and whatnot, and clustering. So yeah, Python is really good package support for machine learning, and that's why a lot of people tend to always, by default, use Python. Most of the project teams use Python, if I'm not mistaken, for actually working on stuff. So yeah. So we're going to use this thing called Keras as well, which is basically a wrapper on top of TensorFlow, and it simplifies a few things. Advantage of that basically is, I mean, it's easier to set this up, but it's a little less customizable. So it depends on your use cases, what level of granularity you want to go to. If you're doing something really simple and you just need to chuck together a neural network, Keras is totally fine. But if you want some more control and fine-tuned things like some of the more baseline, like lower level, I should say, libraries like TensorFlow or PyTorch are probably the better option. So we're going to import some stuff. These are different layers. Last time we did talk about how like a neural network can have different types of layers, and those layers will basically impact how it trains. So we're going to import this thing called a dense layer and also a thing called a sequential layer. And we're also going to import an optimizer, and this is an optimizer called Atom. There's a good handful of different optimizers, and optimizers basically dictate how you're going to do that gradient descent, like kind of minimizing error method. And that's what the optimizer is. You can, as we talked about last time, we can actually add certain things into optimizers, such as momentum, that can help kind of change what they output. So we're going to kind of talk through what building a neural network in TensorFlow sort of looks like, and then we're going to apply it to a case study where we'll sort of think from the perspective of how we would approach this problem if this was sort of a new and novel problem we were seeking to uncover. Dense is just the name of a layer. So a dense layer is basically commonly pretty like it's just sort of this layer where let me see. It's pretty commonly used just in like hidden layers and stuff because it has a lot of like it's like dense, so it has a lot of interconnectivity. Let's just look at a diagram. Dense layer. Yeah, so it's a simple layer of neurons in which each neuron receives input from all the neurons of the previous layer. So yeah, you see how each node kind of sends something to the next node. That's a dense layer. And this image, I guess, if you're curious, this is an optimization. We're not sort of a method known as a layer known as a dropout layer, which can help with overfitting and things like that. But that's for a different time, I guess. Yeah. But it's just very much just like every neuron feeds into every other one, and it's just kind of slap it on there and hope that there is some relation. Yeah, and then there's also a sequential layer. Let's look at what a sequential layer looks like. Okay, so yeah, we're playing stack layers where each layer has exactly one input tensor and one output tensor. So yeah, it's just basically a linear stack of layers. So you stack them on top of each other and just kind of feed on into the next one. But yeah, so we're actually building the model right here. So we're going to say the model is a sequential model. So each layer is going to go here, here, here. It's going to go in a sequence. And so we start with a sequential, we're going to say that this is going to be a sequential model. That's what we're defining here. This model equals sequential parentheses. And then now that we've defined that we're going to have the sequential model, we're going to add a dense layer. So putting in a dense layer. And then we're going to add another dense layer. And then we're going to add a final dense layer with an activation function called a softmax function. And you can see from this sort of dimensionality that we're starting with a sequential layer, and then we have 26 input dimensions to our first dense layer. So if we think about it, we're actually going to use this model for the problem we talked about last time, where we're looking to predict the language that is being spoken based off of letter frequency. So since there are 26 letters in the alphabet, we're going to designate our first layer to be a dense layer with 26 inputs. So each of them is going to have a place to go. Yeah. So those are actually defining the dimensions of the matrix outputs and inputs. So for instance, this dense 128 is basically saying, so 26 go in and then some stuff happens and we get an output matrix of dimension 128. Not necessarily. It doesn't have to be a square matrix. Like a line? Array, one-dimensional array. Yeah, for instance, yeah, it could be like, yeah, one-dimensional array, just 128 coming out. And then they would just kind of feed into the next dense layer, and then 256 things would come out. And they would feed into the next dense layer, and then three outputs would come out. And that three is interesting, right? Because we activate the softmax function, and we say there's three outputs. And that's because our outputs are three different languages. It could be either English or German or Spanish. So just to recap this, last week we talked about how we could possibly build a neural network to predict what language a sentence was in by basically just looking at the sentence and counting the frequency of the letters. And then from that frequency, predicting whether the language is English, German, or Spanish. So hence we see we have input dimensions of 26 corresponding to the amount of letters, and output dimensions of three corresponding to three possible languages. And the thing about these, how these layers work is the input actually has to be the same sort of size. So when we say our first layer is going to be dense 128 and our second layer is going to output 256, the first layer outputs a matrix of dimension of like 128 different sort of nodes. And that's the size that the second layer is to take in. And then through manipulations, the second layer is going to have to spit out 256. And the thing is, I didn't that. So yeah, they're sort of arbitrary, but what they determine is how many trainable parameters you have, right? Because we talked about last time how when you have more nodes, right, you have more things to back propagate over, because like when we compute error, we look at how each individual node affects the error. But when we have more of them, then there's more ways we can tune things. So actually, by increasing the dimensionality, we are basically adding more granularity, like more complexity to what our model can learn. So these numbers aren't really arbitrary, although typically they're in sort of base 2, like 64, 128, 256. And you should actually, when you're training, seek to kind of mess around with your dimensionalities and alter them based off how your problem is looking and how complex it is and whatnot. So here we choose our optimizer to be the atom optimizer, and we designate our learning rate. This learning rate also, we can sort of just ballpark at first. There's one that people will usually use that tends to work. And then later on, when we look at the outputs of the model, once we train it and how it performs, we can opt to tune it later. And the tuning of all of these different parameters is this thing called hyperparameter optimization. So once we train our model, what we can do is basically see how well it performs and then iterate over a bunch of different permutations of input parameters. So we could change how many dense layers we want. We can change what dimensionality of dense layers is. We can change the learning rate. And then we'll then evaluate the model with each combination and see how well it does. And we'll try and find the model that works the best out of the bunch, basically. And then we designate this loss called categorical cross entropy. This is like serving the same function as mean squared error as we talked about last time, but it's a type of loss that's helpful for multiple categories, basically. So when you need to look at how well things are performing and it's not sort of a binary or like a single continuous output, you may use categorical cross entropy. For binary classification tasks, such as if you want to know if something is like a cat or a dog, you might use something like binary cross entropy. Whereas for things maybe like continuous outputs, like that example we talked about with housing price, you might want to use something like mean squared error where you're actually computing directly some sort of like mapping value. But additionally, you can also mutate like your loss function and see how well your model performs. That's different. Yeah, so loss is how we evaluate the error at the end of the day. So like last time, at one point, I think we talked about mean squared error, which is like the prediction minus the actual value squared. And we could see how far away our prediction was from the actual value. And that's basically the loss, like how far off you are from the true value. So we can designate that, and then we'll compile our model, and we can see that TensorFlow has a nice wrapper that just tells us like what our model looks like. So, and you can see that each of these layers sort of contributes to a certain quantity of trainable parameters. So right now, our total parameter size is 37251. But for instance, if I change this first dense layer to like 256, you'll see that now we have much more parameters, that trainable parameters, and our model complexity has sort of gone up, allowing it to sort of learn like quote unquote more complex relationships, but who knows at the end of the day. You have to test it and see what happens. Okay, so let's generate some random data. What's going on here is we're saying we want to generate a bunch of random numbers, and there's going to be basically 1,000 examples, and they'll range from 1 to 26. And that's going to sort of simulate the frequencies of A to Z for just some random sentence. And then we're going to reshape this this list of 1,026 featured categories into a single vector. So this will be a 1,000 by 26 vectors, and it'll basically represent our various sort of frequencies in a machine readable form. Yeah, we're just randomly generating them for the sake of kind of showing what they're gonna sort of do. And you can see here that the first X, so basically the first thing in our fake data set of random frequencies for letters 1 through 26 is this. So the frequency of an A in this randomly generated sample is 0.1614, and so on and so forth. And again, this is just a single entry in the data set, and there's 1,000 of these single entries. So we basically have our 26, a vector of 26 letters, and then there's 1,000 of them. And what this thing is called, this sort of 3D matrix, if you think about it, is a tensor. And I can give you like a little drawing of it, but much of machine learning runs on these things called tensors, which are basically multidimensional matrix, 3D matrices. So let's imagine we had our matrix of letters 1 through 26. What a tensor is basically like, it's going to be a cube of these things. So it's going to be like this. And imagine there's a bunch of matrices, each A to Z. And then there's another one, A to Z, and so on and so forth, all the way to 1000. So that's what the sort of data looks like right now. Basically a big, big three-dimensional matrix. And that's how typically we represent the data in machine learning, because we have sort of repetitive features and we want a lot of samples so we can sort of tell our model what the different cases look like. So we end up with a lot of tensors. And that's why this library is called Tensorflow, because there's a lot of tensors and they gotta flow around, I guess. And then, so we'll call this X basically. Our X will be the sort of inputs in this case, where we have made this 1000 by 26 tensor, 1000 by 26 by 1, I guess, tensor that contains all of our letter frequencies. And then we have Y, which is going to be our sort of outputs. So for each of these 1000 letter matrices, there's going to be a corresponding output. So they all correspond to a language. And that's what this Y is doing. So the Y is going to be a tensor of 1000 by 1 by 3 by 1. And that will basically contain information on the language. So each, basically A to Z, will be paired to an output that's like German 0, 0, or like Spanish, so on and so forth. And last time we talked about how we would encode these different languages as sort of machine readable numbers. And we had decided on this thing called one-hot encoding, where each sort of language has a different representation. So 1, 0, 0, it might be English. 0, 1, 0 might be German. And the last one, 0, 0, 1, for instance, could be Spanish. And as long as we remain self-consistent with those encodings, our model should be able to learn. And basically, we're telling it, how do we map this input frequency list of like 0.07 all the way to like 0.6, representing the frequency of A to the frequency of Z. How do we map those onto, for instance, 010 being Spanish? And that's, at the end of the day, the function we're trying to fit. So we can look at these. So this, for instance, is going to be the first X, these frequencies, and then the predicted language is 010, which we can say is Spanish or something. Does this all look good? Does it make sense? This is sort of your input and your output data. Now, yeah. Yeah, they should probably add up. Yeah, because there are word frequencies and they are like all random numbers within that range. Yeah, so they should, because yeah, they're just frequencies. The first Y is the prediction that, or is the label for your data. So X is the data, Y is the label. So it's basically saying that X is the frequency of letters represented in a sentence in, for instance, Spanish. If we say 010, the first Y corresponds to Spanish. Exactly, yeah. And if we look at, for instance, we can actually look at it. We'll look at the second Y and second X. So this this frequency of letters in a sentence corresponds once again to Spanish. And let's look for a different one. Let's see if we can find that one. Let's get 4. Oh, they're all that. Let's look at 10. Okay, yeah, and now you see that this set of letters at this frequency corresponds to this other language, 100, which we kind of willy-nilly called English. And that's sort of just how our data looks like. Just keep in mind that the X basically is your data and the Y are the labels for your data. Yeah. So, and yeah, as I said, since we're trying to basically fit a function that maps some input frequency of letters onto some language, we have to give the model some pre-existing information that is true so that it knows what is right and what is wrong. So that's why we have our training data and our labels. Our training data is the thing that the model is going to look at and try to find a relation that takes the training data onto its label correctly. And when it makes an incorrect prediction, when it says, for instance, it can say something wrong. For instance, it might say that with its given knowledge, it might create some function that'll take this X matrix onto English instead of Spanish, being 010. And then we'll basically say, we'll compute the loss with categorical cross entropy. It'll say, oh, that's wrong. And then, okay, so the categorical cross entropy function looks a little different than the mean squared error we talked about. And that one is suitable for computing loss in multiple categories. And let's see. But yeah, let me find a good, better one. Yeah, so if you look at this function, it takes a summation over like the amount of categories you have. So it's basically going to look at like how these things look, how your output basically looks in terms of computed over each category. And so it's not only looking at a single one, it's going to look over all of them. And that's why in this case, since we're performing a classification task with multiple classes, we're going to opt to use categorical cross entropy because this is the only thing that'll actually give us the proper loss values for our problem. Yeah.
How we fit our values values the other.
Oh. Oh, yeah. So we talked about the softmax activation function last time. Yeah, and that's what's going to be basically doing that. So let me see. So the softmax basically wants like it's gonna take in, it has like, we're gonna tell softmax function and we're looking for 3 outputs. So it knows in the summation that it's looking to convert this like where's the layer? It's looking to convert basically this so this densler here is gonna take the 256. Here, let me draw it, that might actually be helpful. So what's going on is we have this input dimension of this all the way to this, and this is of size 26. And then what's going to happen is since we've designated this output to be 128, this is going to bounce around to like different like other nodes where it's going to get weights and other biases. So it's going to basically bounce around to these different things where it's going to get a weight and then a bias. And it's going to go all the way down and get more weights and biases. And since we said that this is going to be 128 outputs, this is going to be 128 total. And the same thing is going to happen on the next layer, except it's going to be even bigger. So there's going to be 256. And then by telling it once that we want an output of 3, it's basically going to find a way to squish these all down into like just 3 in the end. And that's going to give us like sort of the proper dimensionality that we can then feed into this softmax function to give us a probability. And that's what sort of like internally it looks like, I guess.
When you're writing
15. Oh yeah, because so for this, we don't really need to use a softmax function because those are just the labels. Those are like the answers in essence. But the softmax function allows us to go from the input 26 to the answers. But we're not actually we're not actually doing anything in the model right here in 15. In 15, all we're doing is like just making the model. I'm sorry, we're making the data and we're making what the labels for the data are. This is the data set we're going to train on. This is basically the ground truth that we know is right. So for instance, in a real world problem, basically what would happen is like we would look at like a sentence, right? And we would count the frequency of the letters. And then somebody who speaks English, German, or Spanish would actually look at the sentence and say, this is English. And that would be the label for that piece of data. So we aren't doing anything ourselves. Like we aren't doing anything computational here. It's nothing with predictions or modeling. This is the ground truth. This is what a human would have done. And that's how we train these models. We have to make data sets for them, basically, where we have like a task we want to do. So for instance, like if we want to do like facial, like face detection in a picture, we would basically have like a human look at a bunch of pictures and say, this one has a face, that one doesn't have a face. And then that would be our ground truth labels that we would train the model on. Does that make sense? Okay. But yeah, so now this is going to be the actual training part. So we're going to use this thing called sklearn. So that's one of the very helpful Python packages that can help us train and test. So we're going to make some training samples, some tests, and some testing samples. So when we basically train our neural network, we segment our data into a couple that we're actually going to feed into the model for it to kind of train and back propagate on. And then we're going to segment another small test called a test set that we're going to evaluate the model on. So we're going to train our model on that first bigger training set. And then in the end, we want to see how well it's doing. So we're going to make it basically label the test set, and then we'll compare those labels with the actual outputs of the test set. And we're going to do that. And I'll try to explain that a bit more here. So our model trained on these train sets, and then it performed evaluation of the test sets. However, we know what the true answers to the test set is. So we can compare what our model says to what we actually have and compute some accuracy this year. And the accuracy kind of sucks. And we actually usually always want to segment a testing set out that doesn't overlap with our training set, because it's quite dangerous if we're having our model basically test itself on something that we already gave it to learn off of. So that's one thing to keep in mind. And that's why we have this pretty handy train test split functionality in scikit-learn. So yeah, always you want to have a train set and a test set. One to learn on, one to check your progress on. It's like if I gave you like a reading or like a problem set to do, but then when I wanted to check how well you were doing in the class, I didn't give you a new test, I just gave you that problem set again. Yeah. Oh, that's weird. Like in here. Oh, that shouldn't be the case. Like if I put in x21 and y21, I have a different y and a different x now. So that's strange. No, you shouldn't have to. You just have to run this cell, and it should give you the right thing. Is it looking fine now? Okay, perfect. But yeah, so now to actually train the model, we call this function called model.fit. We give it its training parameters, its training data. We give it its training labels. And then we tell it this thing called epochs, which we briefly touched on last time, basically how many times to iterate over this process. And then we give it a batch size, which is kind of similar to what we talked about in stochastic gradient descent, where we're not actually going to compute loss on like every single thing, or else that would take forever. We're going to only do it on 32 samples, for instance. No, this is like, in stochastic gradient descent, we said that oftentimes in like the baseline SGD, we pick a random sample and we just look at it, but sometimes that's really skewed. So we can designate a batch size. So we can look at like 32 samples, but it's 32 random samples to sort of help even out and prevent skewness. So in that case, this is what the batch size is doing. Just what you tell it in the batch size. So 32 samples. Yeah. So you're gonna basically like back propagate with 32 out of your, for instance, 1000 or however many input pieces of data you're gonna give it. Yeah.
Like all these calculations, basically running the ownership of the process is done by the train test split function.
No, so the train test split just divides up your training and testing data into X train, X test, Y train, and Y test. So all the train test split does is it segments data.
What is actually
Model.fit runs all the calculations. Yeah, that's where you actually fit this model. So we can actually look at what train test split does. You see here how our X shape was 1026. We called train test split, so let's check X again. We can do X train dot shape, and we can do Y train, X test dot shape. And let me actually put some statements around it because I'm not sure what will happen. Oh, that's strange. Oh, it might be because X train and X test aren't NumPy arrays anymore. They're scikit-learn, like some sort of object. But we'll see what happens, I guess. I'm still gonna naively do it. Yeah, fit's a method that's fit is a method that's a part of your model. So when you do let's see, when you do model equals sequential, you basically like instantiated this model object and it has the function fit that you can call on it. But yeah, so you can see that by calling train test split, our X train size and our X test size are different than what they were here. So it used to be 1026, but now it's 75026 and 25026. So that means we're training our model with 750 of our data samples, and then we're testing it on 250. Yeah. And you can also manipulate this train test split to give you basically different, fractions of data. So you can do like 0.9, 0.1 if you have like not that much data and you want to save as much possible data to train on, stuff like that. So it's pretty extendable. You can modify it however you like. Yeah, it's pretty sucky. And yeah, so actually, we didn't think about this. Why might it not be super accurate? How did we actually make this data? Right, it's nonsensical, right? We didn't actually take sentences and take labels and build this data set. We were trying to use it as a toy model and we just made a bunch of random crap and shoved it in there. And it doesn't really map on anything, right? It's just random 26 dimension vector, random 3-dimensional vector of 1, 0, 0, 0, 0, 1, 0, or 0, 0, 1. And it can't really find a great function to actually map our random nonsensical data on there. So actually, this is a decent demonstration of the fact that random number, that package actually makes random things. Yeah, because it would actually be kind of suspicious if random number made two sets of random things that for some reason had a mapping onto one another. But yeah. Actually, in this case, so initially when we start our model, like when it first starts training, you know how earlier last time I'd said that it just instantiates weights and biases at random? You would expect like a 50% accuracy initially, but actually it looks like here it's getting worse, and it might be because it's trying to figure out some relation. So it's tuning itself and moving around, but it's like just not doing well, and it can't figure a way out of the rut. Yeah, so it's kind of sad for this poor little. Yeah, so we've given it like a fundamentally unsolvable problem because our input and output have no relation, but we're telling it to try and learn a relation. So we're just kind of kicking it. But yeah, if we look at what's going on here, This epoch is your epoch number, which is kind of what we set in that parameter. Sorry, in the arguments to model.fit. This time here is basically telling you how long it's taking. And then this is the same thing. This is the loss calculation, what value it's getting. And then this accuracy is what it's evaluating when you have it test itself on the testing set. That's what I talked about like earlier, where you have this test set. So after it goes through that training phase, it's going to try and predict the outputs of the test set. And then it's going to compare how well it did against the labels that we know are true. And yeah, so you can see here, it's not doing super hot.
The number of outputs the model got right.
Exactly, yeah. And okay, so here's the explanation of why this model. Oh, yeah, okay, sorry. So we had set, so for binary classification tasks where it's a 0 or a 1, we would expect a random guess to be a 50-50 chance, right? But in this case, actually, there's 3 categories. So we'd expect a 33% accuracy if it's just randomly guessing. But somehow it has almost like a 40-something% chance. So it's actually doing better than randomly guessing, right? So actually, maybe we shouldn't kind of slander a model too much. Yeah, I got hung up on the fact that it was binary, but it's actually not binary. There's 3 categories. So it's performing better than just a random guess, which may seem a little suspicious, right? Because we've supposedly instantiated random data. But basically what the model is doing here is this thing called overfitting. So overfitting is happening, right? Because overfitting is this thing where basically the model hasn't learned necessarily a relation, but like the correct relation to extend itself to other tasks. It's figuring out a way to kind of draw this weird function that'll encapsulate a good amount of data points and get a good accuracy. So what do I mean by that? Well, visually, I can show you like this. So let's say let's look at this in terms of like, yeah, go ahead. Not necessarily, but this is like maybe something to read up more on later, but there's actually ways to by visualizing the loss of the model and how its error and stuff changes over time while it trains. You can look at you can examine visually if it's overfitting or not, but it's not a hard and fast rule that if a model is doing better than we expect, that it's overfitting. But yeah, so this is what overfitting looks like. Let's go back to that sort of idea of trying to fit a regression that we talked about earlier. So let's say we had this spread of points. And sort of the ideal regression that we would fit for this is something like this, right? Now, in this case, we're using a neural network, and it has a good quantity of trainable parameters. So it's pretty smart, right? It has a pretty big capacity to learn complex relations. Now, the problem is, given the amount of data we've given it, the model might be getting too smart. And the model seeks to minimize error, right? And when we do a regression like this, we still have a little bit of error, right? Because it's not exactly hitting all the data points. So the model might actually plot this regression, and then it might decide, oh, I can come up with a better way to get less error. Well, the model might decide that since it is so smart, it might try to do something like this. It might fit a function because we've given a lot of nonlinearity and a lot of complexity. It might fit a function that looks like this. And the green line would give a better loss, than the actual correct regression, but it's fundamentally wrong, right? Because maybe a better illustration is it fits a function that looks like this. Sorry, go back. That looks like this, like some weird periodic function that looks like that, because that happens to hit a lot of the points and have very low error. But when we actually ask it to perform like a regression, right? And we give it some more points, maybe they happen to distribute like this. In the case of our regression, it would kind of do a pretty good job, right, and draw a line through. But our weird, windy, overfitted function is just going to go like this, and now like miss all of them, for instance. And that's why overfitting is bad, because you've given the model some training data and some testing data, and it's somehow figured out a weird way to kind of create a function that minimizes error on them, but it hasn't actually learned the proper relation. It's just learned, it's sort of cheated the system, right? It's like a kid that like if you like give it a test, it memorizes the exact answers to the test. And so it can circle like A, B, B, C, A, and it knows that that's the right answers, but it can't, if you give it another question, it's sort of not gonna be able to answer because it doesn't actually know anything. It just knows what the answers are at this point because we've like trained it so much and so repetitively on a fairly simple task. Yeah, yeah. Yeah, and overfitting is a pretty big problem because it can deceptively show like high accuracy when in truth, when you give it a new thing, the model is going to fail. And that's why it's always good to sort of not take some of these numbers at face value and to always test and look at things and like yourself and see how they're doing. And so, yeah. So when we actually test it, we see its accuracy is about 0.3160. So it's not too good. And like on the actual testing data that's never seen before, we can see that it basically is the same as random. And that sort of confirms our suspicions that it's overfitting, because even though on the training data, it was able to get some accuracies that were higher than random guesses, when we gave it new data, we gave the model a new question, it doesn't actually know anything and it gets the question wrong.
It's actually overfitting, or maybe the point is just like an outlier.
Yeah. So that's one thing you want to address in your data cleaning early on when you're preparing your data set. Typically, we'll want to we'll like visualize your data, look at how clean it is, and then we'll remove outliers from it so it doesn't sort of do things like this. Yeah. And this evaluate basically is so our when we trained the model, it generated a function to map our input vectors onto an output answer, and evaluate basically performs that function on this X test and Y tests and allows us to verify how well the model is doing. But yeah. And then now we can try and build a different model. Okay, wait. I actually misspoke over here. So I got the earlier part confused with the next part. So earlier here, the accuracy, this accuracy isn't from the test. It's from just the data itself, where it's segmented, like it's just looking over a part of the data and then computing the accuracy. If you want it to do these accuracy tests on a small partition of the data, you can call this thing called validation splits. So this is what happens down here. So yeah, so this was the test data that we evaluated our model later on, and these accuracy things were all generated from the training data. But typically, we actually do this thing called validation splits. So we divide our data into training and testing, and then we do a validation split. So we have a validation accuracy. So that's saying out of our training data, then again, segment 0.2 out of the total to use as validation data. And so that way, the accuracy, since the accuracy is looking over, it is like looking at the loss and the errors in the, like when we train, when we use a validation split, we aren't reusing training data to test during our actual epochs. We're using data the model hasn't seen. Not necessarily, because like as we said earlier, the model hasn't. Say again? Yeah, but because we've overfit, we've managed to get an accuracy over random guessing. And that's why here the accuracy looks so looks higher. But then since we're doing a validation split, so we're pulling out a part of the training data that the model hasn't seen before to actually validate on. You can see the validation accuracy here is like akin to a random guess. It always hangs around 0.3. And that's why like typically I'd recommend when you are training your own models to use a validation split, because you can sort of spot this issue of overfitting earlier. So to that point, this is what I was going to say when I was talking about you can actually use visualizations to see when a model is overfitting. So when a model is overfitting, what's going to look like is your regular loss in accuracy, so your training loss and training accuracy, which is computed based off data the model has seen, that's going to continue to decrease. It's going to get lower as you iterate, but your validation accuracy, which is done on, testing performed on data the model has never seen, it's always going to stay around the same. So when you look at a graph of neural networks and you want to know, for instance, like I'm doing these epochs, maybe I'm overfitting after a certain epoch. What I can look at is like, let's say at the start, right, my validation loss and my training loss are both going down together. But maybe at epoch 3, my validation loss flattens out and my training loss continues to decrease. And that basically means at epoch 3, I am now overfitting, right? Because the validation accuracy, the accuracy that's obtained from looking at data that's not being trained on, has stopped getting better, whereas the training data is still getting better. Validation that's performed on the training data is still getting better. Does that make sense?
Well, it's basically like training this network on a sort of different part of the landscape, or
no, it's just doing the same thing but 5 times. But it'll retain what the model has learned from the previous epoch. Yeah, exactly.
So it would be like essentially the same thing if we ran, say, epoch 1 just 5 or 5 times.
Exactly. Yeah. If we just decide to train our model and then we save it after the first, like after 1 epoch, and then we load it back in and we train it again, we just do that 5 times the same as doing it for 5 epochs. Yeah. And yeah, I kind of like misspoke earlier, so I'm going to recap everything so that there's no confusion. So earlier when we didn't designate a validation split, this accuracy, so accuracy itself, accuracy and loss, not slash, accuracy and loss, those are results from let's see what's a good word to use here. Results from training data. And they can be deceptive, and they can mean, even if they're decreasing, they can mean the model is overfitting. The validation accuracy and loss is results from validation data the model does not train on. And then finally, we have testing accuracy and loss, which is, or testing accuracy more so, which is basically partitioned part of overall data set that model tests itself on. So actually, in essence, the testing set and the validation set are very similar things, but the validation set is just much smaller, and it's just like a little metric we use after each epoch to see how our model is doing.
So we want to like stop running the neural network after the validation reaches the same level as that.
Not necessarily, because if the validation and the accuracy are the same, like there's nothing like wrong with that, but we do want to stop it when the validation loss stops decreasing, and so there's some cases where we might want to stop. when accuracy and validation stop decreasing, for instance. Sorry, yeah, validation accuracy and regular accuracy stop increasing. We would also want to stop if validation, if regular accuracy is still increasing, but validation accuracy has stopped increasing. That means we're overfitting because the model is able to be accurate on data it's training on, but it's not able to be accurate on data that's not part of the training set. And there are actually sort of built-in checkpointing methods that you can kind of tell the fit process to say like, hey, once we see like any of those signs and stop training, kill it off, and then just retain whatever you had then. Yeah. But yeah, and then we can actually call this predict function to classify data. So here we've generated an example, basically a 1 by 26 matrix, and we can have our model predict what language it's going to be in. So here we see we have 3 probabilities, and they designate how likely it is that this input vector of 26 letter frequencies will correspond to a certain language. And so it's saying the highest probability of this random input vector is 47% for I guess, German language in this case, since we had said English was 100, Spanish was 010, and German was 001. So this is what this predict function means. And then, yeah. And then, so yeah, if we want to look at it as a single class, then we can just basically get the maximum. And it's saying the maximum is index 2, so 0, 1, 2. The maximum likelihood for the language is our third category, which is German. And this 2, I mean, the 0 indexing kind of makes talking about it confusing, but this 2 corresponds to this index. But yeah. And now we've trained a model and we can make predictions with it. I mean, yeah, we've just basically trained a neural network. Now we've given it junk data that makes no sense, but I mean, yeah, we've done something. We've done something with it. So yeah, we have built a neural network. Oh yeah, it's super simple. That's what like I usually say is like, I think we really ought to be encouraging people to kind of just go out there and look on like the internet, just to look at tutorials and stuff. Because these things that like, you don't really have to have like a mathematical understanding. Like we could have not talked about anything we talked about in the past workshops, and we could have just started here, right? And I could have just told you that if I put some random letters in a sequence and I call these nice and wrapped up functions, I can optimize and try and get something that's accurate, and I can be happy and call it a day. And I can have no idea why I did that, but I mean, I can have something that does the job, you know? And I mean, that's why like a lot of the implementation, like why these things are so popular as well in like modern day sort of tech or like different applications is because they're so easy to build nowadays. Yeah. Yeah, so what you would do there is, one technique is you could just convert the images all to their pixel values. So but the thing you would want to be aware of there is you need your images all to be of the same dimension. So you know how there's resolutions for images? Like they would also all have to be like 300 by 400. And they would also have to be like of the same frame size, or else you're going to have different numbers of pixels in them, and that dimensionality mismatch is going to bug out your model. But yeah, you just, all these different things have encodings for them. So for instance, if you want to feed languages and words into neural networks, there's these things called word embeddings and encodings, which basically take them to different like numbers in a matrix. Yeah, what's up? Question? Oh, okay, gotcha. Yeah, so I mean, yeah, it's basically, we have a lot of different ways to map different things onto like numerical representations that a machine can learn. So on this next couple of cells, there's just a bunch of stuff on different types of neural networks. I'm not really going to cover this at all. You can just sort of read about it later. This is a pretty good overview of just some of the common kind of neural networks that you see a lot nowadays. GANs are used a little bit less. They use a lot of, I guess, used a little bit less in some of the more like well-known applications, but they're used for generating a lot of different images, generating new images, generating new things. These transformers are used a lot in natural language processing. They're probably one of the biggest like language generation and encoding kind of models. LSTM also used a lot in natural language processing. CNNs more so in computer vision, and these MLPs or multi-layer perceptrons. At this point, I think they're kind of obsolete. They're very basic. They're sort of like what people thought of at first when we were kind of first developing neural networks. But that's a side point. Let's look at a sort of case study where we'll try to make a neural net to complete a task. And in this task, we want to predict whether patients died from heart failure within a certain time frame from their last check-in. And why might this be useful? Well, we can figure out if somebody might just straight up die of like heart failure, right? And we're postulating that based off of some different inputs, such as their age, if they are anemic, if they have diabetes. I mean, I don't know what these words means, but I bet it is some disease or something. But if they have like high blood pressure, like do these factors somehow all get smushed into a function that allows us to accurately figure out if this person is going to have heart failure or not? So this is the task we're going to give to our model. And so we have this heart failure prediction data set. You can find a lot of different data sets just by Googling them online. And they'll usually be in this file format called CSVs. And you'll have to do some data exploration and pre-processing to get them machine usable. So you can see here that our heart failure prediction data set has a bunch of labels. So we have age, we have whether they're anemic or not, the amount of creatinine phosphokinase in their body, I assume, whether they have diabetes, whether they have, I have no idea what ejection fraction means, but whether they have high blood pressure, like stuff like that. And so these are basically our inputs. Now, we can think about how these things relate to heart failure. And if we personally believe that some of these parameters don't matter to us, we can actually drop them to simplify our task, because basically the less inputs that are like not useful to our prediction output, if we can manage to remove those, we can basically reduce the noisiness of our input data. We can confuse our model less. For instance, let's go back to the learning analogy. Like if you were a kid in school and you're preparing for a physics test, it would be like stupid for the teacher to randomly teach you about like, I don't know, cooking in preparation for your test, right? Because that cooking knowledge isn't actually going to have an output, like have an impact on the output, which is you solving a physics question. And so that's analogous to us dropping certain columns of a data set that we believe aren't going to be helpful for us in learning and in our model learning. So yeah, we have this data set. And then we have all these inputs, and then we have one predicted one label, death event, whether they died or not. Yeah. Mm-hmm.
And I draw like things that I think are like correlated, but how much the correlation of like high correlation down like more like dropping correlation?
Yeah, so we'll actually talk about that in a sec, but I'll go over that when we look at the correlation matrix. But yeah, so we have 12 features, all of this gibberish, and then we have a death event, whether they died or not. And we can do that, and then we can visualize them. So we can look at how these correspond to death variables. So the blue here is death event, 0 or a 1. So if we look at this graph, for example, we can see that people who had higher, so for the majority of people have lower creatinine, I'm going to call this CP. The amount of people who had lower CP is typically pretty frequent. So the usual average person has low amounts of CP in their blood, I guess. But there are very few people who happen to have a lot of CP in their blood, and those people tend to be more likely to die of heart failure. That's what this histogram is saying here. we can look at something like, let's not look at ejection fraction because I don't know what that means. Let's look at something easy. Like, I think platelets makes more sense. So like, for instance, when we look at CP, right, it's pretty obvious. People who have less CP tend to not die. But if we look at platelets, it's a little less clear, right? People who die have varied amounts of platelets in their blood. And what might this mean? Well, this might mean that this variable may not be super helpful for our prediction, right? Because there doesn't seem to be any sort of easy segmenting between like how platelets might map onto death event. Like you may be just as likely to die if you have this amount of platelets versus that amount of platelets. It's very spread out. It's unlike CP where we see quite discernibly that you're going to have, if you have more CP, you're more likely to die. So we can maybe say that platelets isn't a very good predictor for death events, and we might choose to drop platelets as a input parameter when we're actually training a model. Does that sort of logic make sense? So yeah, these are histograms. And then those are for continuous variables. We use histograms because they kind of can go along all the way on the axis. Now, for our sort of binary variables, like if somebody has diabetes or if they don't have diabetes, we're going to use a pie chart. So we can see if somebody has anemia, then if you have anemia, you have 40.9% of them are this orange. So 40.9% of people with anemia are in the death counts, and then so on and so forth in the survive. This is survived and this is died. So if you had anemia, then 49% are in the 1. And then conversely on the death, you can see that you have the similar setup. And if we look over a bunch of them, you can see that they all look pretty similar. So what does this mean? Well, this means that each of these variables, like none of these variables provide sort of super distinctive kind of information about death, like whether somebody's going to die. They all look very similar. So that means there may not be like a super like significant in comparison classification variable. And that might make the task a little bit more challenging because it's not as clear and obvious that something might be a really, really super big indicator of what it's going to look like. But yeah, like, so for instance, like the amount of people who have, who didn't die, like this composition has anemia, this composition doesn't have anemia, this composition does. And I mean, it's not super significant, it's not very interesting. These statistics all look roughly the same for all of these things. So perhaps these categories do not directly give us any sort of predictable output on death or no death. And that's problematic for us, right? Because it means it's tougher for a model to learn a function if things aren't super clear and obvious. And so we're going to do the same thing. We're going to generate the train test split. So we see here we have 239 training examples and then 60 ones that test on later. And one thing that might be a bit concerning is if we look at the continuous variables, they have different values, right? Some of them are really big, some of them are smaller. Why might this be a problem when we're actually training our model? Exactly, right? The larger variables, I can't talk. The larger variables are going to skew the results, right? Because they're just bigger. They're going to sort of overwhelm the smaller numbers. So what might be a way for us to overcome that while still keeping significance in the representation? Say again? Not in this case, right? Because the median of the larger variables is still going to be bigger than the median for smaller variables. Yeah, we just want to scale all of them. We're going to normalize all of them between 0 and 1. And that way, like a large variable won't completely blow up something. A small variable might be still relatively insignificant, but it's also not going to completely distort how things look in terms of our continuous variables. So what we're going to want to do is scale our variables, our continuous variables. And that's what this function does. We're going to once again borrow from scikit-learn and use standard scalar. to perform normalization on our variables. So we're gonna basically apply that. And if we look at it now, we'll see that all our variables are now between our desired values of -1 and 1. We're gonna set them between that because some things might be negative. So we don't want to binarily like squish them all to 0 and 1 and accidentally pull up things that are like we don't want to cause errors with negative values. So in this case, we choose -1 and 1. In other cases, you might want to choose to normalize between 0 and 1 and so on and so forth. But you can see now upon applying that, we do have our desired matrix input. Does the logic and why we did all this stuff make sense?
Yeah, I'm just wondering, like, how normalizing it would help to sort of reduce the skew from the become smaller.
Yeah, okay. So let's say, for instance, we had like value A, it's like 2, 5, blah, 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 blah. And B was like 3, and then C, maybe that was like a happier medium that was like 3,000. So since these are like, if we look at our earlier model of like W A X A plus W B X B plus W C X. In this case, this 25,000 is going to be really, really big. In this case, it's going to be 3, and that's 3,000. So what the values that we're going to get on the output are really going to be skewed close to 25,000. Now, if we normalize it, and let's say it's between 1 and -1, this might be like, and let's say we're going to squish it between -1 and 1. And our biggest value is 25,000, for instance, then maybe the 25,000 is going to be like a 1 or something. And then this 3 might get like really tiny. And then this 3,000 might be in the middle, like it might be like 0.01. What this allows us to do is like our model is still going to be able to sort of understand that certain things are bigger than other things and how that works. But now it's not going to have its values explode. So its value is going to be like 1 point something 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 instead of like 25 something something something. And that's going to help us in both back propagation, so we aren't computing like huge things, and also just keep everything sort of on a similar scale that is like not nonsensical. Because like we talked about last time, I think when you don't normalize stuff, you basically have this continuum and you don't know how big things really are. So if we squish them, we basically have better knowledge. Yeah, and then so our Y data is binary. So we know this is a binary classification task. Either you have heart failure and die, or you don't and you live, with living being 0 and dying being 1. So then we can encode all of our death or no death into a matrix. So this is going to be, for instance, these are going to be all the labels. And you notice how there's 239 of them corresponding to the 239 12-dimensional vectors that we have for our inputs. And we talked about the overfitting problem. So this time, to avoid that, we're going to use this thing called dropout. So the dropout is a special type of layer. I actually kind of looked at it briefly because we Google imaged dense layers. But what dropout basically does is it takes a subset of the weights in a layer and it sets them all to 0. So basically it says, you're not learning anymore. Like this section of nodes is not going to learn anything. And why might that be helpful? Well, we basically forget what we learned on those nodes, and that forces the model to retrain and relearn the relation. So this basically is telling the model that, okay, so you got all this information, forget it, and learn it again. And that instills like a deeper understanding of the data in it. So instead of repetitively droning it on and on again on this sort of method maybe that it had of learning, it's going to have to try again basically and try to relearn that pattern in a good way. And that helps overfitting because it makes it so the model isn't just kind of continually like pumping away at this one sort of optimization as it tries to update its weights and biases by smaller and smaller amounts to kind of try and eke out marginal gains in accuracy. And that helps it from kind of also becoming way too granular and doing this. Let me see, doing this thing, because it might be really smart, right? But maybe it learns this much, like it learns to draw a line like that, but it's forced to forget everything. And then to actually arrive again at a good set of weights and biases to allow it to classify things accurately, it most likely will have to find a better way of learning the data, because it's pretty highly unlikely that it'll arrive at the same thing twice. That happens, like it's very unlikely that it'll overfit like exactly twice if it's forgetting a set of weights. And that's why we use the dropout layer.
Or is it only one of the weights?
It's gonna forget like a proportion of weights that we can actually tell it. So we're gonna tell it drop out 0.3. So it's gonna forget 0.3 of the weights in this dense layer. So that's how it's doing it. But we actually don't know that the dropout will 100% be beneficial. But like, for instance, if we train a baseline model and we look at the graphs and we see, oh, our validation accuracy has stopped increasing while our accuracy is still increasing, then maybe you want to stick a dropout layer somewhere, like after a layer, and see if it does any better. And if it happens to do better, then like good, our dropout layer worked. And if it didn't, then something's still going wrong. We have to keep testing, keep trying. But yeah, we're gonna import our dropout layer and basically do the same thing as we did last time. We're gonna define our baseline model. So you have, like we were doing the exact same thing as last time, except we have more layers this time. We say our model is gonna be sequential model, so layer, 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 layer to output. And then we're gonna say first layer is dense 64 with input dimensions 12 because there are 12 features. And then we add a dropout layer there to prevent overfitting. And then we do all the same things. And this time we say our activation is sigmoid. Since we aren't doing multi-class classification anymore, we don't want to use the softmax. We use a sigmoid, and that's going to do the binary between 0 and 1 thing. Once again, we set a learning rate, and we use binary cross entropy loss instead of categorical cross entropy loss, because once again, we are doing binary classification. And then we compile our model, and we can look at it once again. And we can see that it looks like this. This is how the layers kind of flow into one another. And we can call fit. And notice how, since we have less data this time, we're going to use a smaller batch size, for instance. That's one way you can permute things. And then, oh, you can see the accuracy here. It hasn't done too bad, right? It's hitting around like 75 to 80%. Now, we don't know for sure because we want to first test and see how well it does. So we're going to apply it to our testing data. And no, didn't do as good, but 70% is still better than a random guess. Okay, yeah, it hangs around that about. So one thing that's interesting to note is that your model is going to actually, it's not going to be deterministic. So every function it generates is going to be slightly different. That's why you see like when we train this one, these numbers are different. And then when we reevaluate it, the accuracy is different as well. And that's why in the first, I think maybe it was one of the early sessions, you talked about this thing called setting a seed. And the seed basically says, like, it's a label basically for randomness. It's going to say, hey, do this random process exactly the same as last time. So if I say like random seed equals like 47, and then I give my model.fit a random seed, and I give it the same one over each iteration, it should train the same way every time. But if we don't tell it that, it's just going to do it's going to do whatever every single time, because it's going to always instantiate different random weights and biases. It's going to do different random things. And thus, it's not going to be deterministic. And that's why we're seeing different accuracies. And then, yeah. So then, oh, so this is a little demonstration of what accuracy you would get if you just guessed how well it was doing every time. And honestly, it's kind of concerning because this random guess accuracy is like 0.67, like 9, and this this trained accuracy is 0.7. It's not actually doing that much better than a random guess, but oh well. It's not actually overfitting because, like, I guess in the case of just 50-50 guessing, it's not doing, like, it's doing about the same. I mean, sorry, it's doing better than random, like if you were just to randomly assign 50-50 guesses. This thing here is kind of like not exactly 50-50 guessing, but, and that's why it sort of looks like that. But yeah, it may not be necessarily overfitting because, let's see, if we train, we see that our validation, our test accuracy isn't super far off from our training accuracy. We can actually investigate that a bit more. We can do that same thing that we did. Let's see. We can do that same thing that we did here with the validation split. So we can maybe look at its validation accuracy over time. And then we can get a better glimpse at how it's actually learning data that it's not training on. So yeah, we'll say this time validation split like equals 0.2 again. And then we'll fit this model. And oh yeah, so actually validation accuracy is not getting any better. I mean, though general accuracy isn't getting any better either. So that may not be a sign. But what this might be telling us is that if you see accuracy isn't getting better, maybe that we don't have enough data, to train on, which definitely is the case here because we don't have that many entries in the column. But we can also maybe try again by only doing one epoch, because you see here it's not getting any better after other epochs. Yeah, you have to basically look at or you won't know in advance. But what I typically would recommend, like what a lot of people do, is maybe they'll say, "Oh, I'll just run this for like a really big amount of epochs, like 200 or something." But I'll have like a cutoff where my model will automatically stop training once it hits like a certain trend. So for instance, maybe the accuracy and the validation accuracy stops decreasing. I'll just cut it off at whatever epoch that was. Or if like you can see that it's starting to overfit, cut it off at the epoch. And more epochs leads to more possibility of overfitting because you're training on the same data over and over and over and over again. So decreasing epochs can be a way to combat overfitting. But yeah, it's not all too good, this neural network, but that's fine. So it's basically when it like takes our testing values and it predicts based off what it learned, it's only getting them right 0.7% of the time, which is slightly unfortunate.
So guesses which are important.
Oh no, so this is computing given an input with this, like with these parameters. Like if I have a patient with a profile like this, will you die or not? Like in the next couple of months. Yeah, that's what it's sort of doing. But yeah, I mean, it doesn't do that well, but we built a model, right? We built a neural network. And you can see here, it sort of incorporates all the different things we talked about this semester. The stuff on like training data, testing data, like epochs, what loss is used for, like back propagation, the optimizers. So this is sort of the final culmination of everything. We have this neural network that makes, albeit not great prediction, it does make a prediction. Yeah, what's up? Accuracy is from the training data set. That's where it checks itself on the training data. And that's why it might not, that's why purely looking at accuracy might not be good because it can overfit. Yeah, that could just be the case, right? Because the model just happens to be able to fit the validation data better. It's sort of non-deterministic how that is split up and what it happens at C. So that can definitely happen. But yeah, I mean, it's a neural network. That's how you build a neural network. You can see, I mean, it's like in terms of code, it's not too tough at all. it's well wrapped. But yeah, any questions on that?
So you can like most of the correlations.
Yeah. And I actually, so we didn't talk about the correlation matrix in this notebook. I think that was an earlier session, but I can talk about it more here. So the better, maybe the reason that we're getting poor predictions is like, well, A, we can see that there's like, it might be tough because these categories aren't great. But B, we might be skewing, we might be getting skew, like we might be getting noise from poor predictors of heart failure, kind of like being introduced as training data. So if we were to drop those columns and drop those training data pieces, perhaps we might be able to figure out a function that does better because we've parsed out some noise. And yeah, I would actually like to talk about correlation matrices for a second. I think we might have actually skipped over what they were in like a previous section, but let's see. Let's look at a simple one. Correlation matrix binary. Okay, that's not what I was. Oh yeah. Okay, here we go. So this is what like a very simple correlation matrix looks like. It's this thing that's used to basically tell you how well something is like accurately predicting. So you see here you have like this is what these axes mean. So +1 and +1 here. This is your actual value. This is your predicted value. So you would expect in an ideal world that if you have a perfect predictor, if something is predicted to be a 1, it's actually a 1, right? So let's say we had 20 data samples and 10 were positive, 10 were negative, and we had a perfect model that could always accurately predict those samples. We'd expect to see 10 in this positive section, and then 10 in this negative section. So actual negatives are predicted as negatives, and we would expect to see nothing in these two sections. Because what that means is, for a model, if we predict a negative, but we predict a negative, but the actual value is a positive, so it's getting it wrong. And then here, the same thing. Our model is predicting a positive, but the actual value is negative, so the model is getting it wrong. And correlation matrices, these columns, like in this binary case, have different labels. So there's a true positive, which means something is actually positive, it's predicted to be positive, it's correct. A true negative, something is actually negative. And then we have false negatives and false positive. So basically, you falsely predicted something to be negative when it was actually positive, and you falsely predicted something to be positive when it was actually negative. Does this binary case sort of make sense? And we can expand that and look at more complex ones. And so this is a multidimensional one, for instance. Like we were saying that, let's see. Yeah, that. So this is a really big correlation matrix of how different parameters in a data set are predictors of one another. So for this instance, it looks like this is about the Titanic, where like your different, like if your class, your sex, your age, your ticket item, your ticket price could be predictors for if you survived or not. But we can examine how the different input parameters are actually correlated to one another. So we can see here that ticket price and ticket ID, these two elements have a decent correlation. That's what this is saying. There's a 0.64 correlation between them. Same here with port. So your port and your ticket price are tied together. So what might that possibly mean? That might mean that if you have a high ticket, if you have a ticket that's expensive, you might always be going to a port that's like a good and like well-maintained port. Similarly, ticket price and class have a strong correlation, which is what we would expect, right? Because if you're of a higher class, then you're going to be able to purchase a more expensive ticket. And notice how the columns here are all 1. And why is that? Well, these are just the variables themselves. So port should always have a strong correlation to port because it's the same thing. Same with ticket price and ticket price. If this wasn't 1, then you built a broken correlation matrix.
But then, so it's symmetric. Right? Because like if you I don't know, like look at over the like class.
Yeah.
Age and class.
Yeah, because like you remember earlier how 1 was actual and 1 was prediction. So in this case, this is feature and this is target. So if we give as input age to predict ticket ID, then we have this correlation. But if we give ticket ID as input to predict age, instead we have no correlation. It just basically means what is the input and what is the target. And in this case, they're not equivalent, right? Going from one to the other might not be the same as going from the other, like going backwards. Let me see if there's a good like examination of that to show the effect. Maybe not. Yeah, these are all like, a lot of them are sort of reversible. But yeah, they aren't always going to be exactly the same because going backwards isn't the same as going forwards. But yeah, I just wanted to quickly cover the correlation matrix since it's a pretty important thing that I don't think we've touched on. So at least when you look at like a guide or something and asks you to make one, then it sort of makes sense.
Class and ticket price are very class and 19.2.
Oh, that's interesting. Yeah, because that might mean that like people who are like, I'm not sure. Okay, so this is feature and that's target. So we're saying that given an input class, what is the ticket price? So that might mean that like even though you're rich, you might still be flying like economy instead of first class. So they might be like more frugal. Whereas people who buy expensive tickets are always going to be of a higher class. Whereas the relationship isn't reversible. So that's like that. Yeah, that's a good demonstration of why going backwards might not always be the same.
Yeah. Correlated there, is there that relationship other than just dropping one column?
Typically, we just drop one. Yeah, I'll actually touch on that right now. So, for the model, right, we don't want to overburden it with information. So if we can give it less features, we always want to give it less features. So if we notice that two features are highly correlated, like ticket price is a predictor of class, maybe we only need to feed the model ticket price. Maybe we don't have to also give it class, right? Because they sort of tell us the same information.
Like, if the ticket price, then it's pretty accurately predicts class, but like it doesn't work the other way around. So we need to drop the variable that's in the target slide in that case.
Yeah, in that case, you would be dropping, let's see. So ticket price is a good predictor of class, whereas class is not a good predictor of ticket price. In that case, I think you might, let's think about it. So knowing ticket price allows you to know class, but knowing class might not let you know ticket price. So in this case, you would probably want to drop class because by knowing ticket price, you know class, but then class might not give you the same backwards. But when we look at data initially and we perform data exploration, the correlation matrix enables us to understand these things and allow us to know, like maybe we want to drop something to simplify the inputs into our model. But yeah, that's just sort of the final thing to touch on. And the correlation matrices are also useful. For instance, that binary one I showed is useful for looking at how your model is messing up. So if your model gets stuff wrong because it predicts a lot of negatives, then you know maybe like there's something like you might have an imbalance in data. You might be giving your model too much negatives. If your model is getting a lot of the negatives wrong, then you might have an imbalance in input data because you're giving it way too many positives. So it learns positives better than negatives because you've given it like a lot of info on it. Let's like think about this in terms of the learning analogy again. Let's say I'm taking a test and there are two things like there's two main categories in the test, like a computer science test, maybe there's data structures and there's algorithms. If my algorithms class has covered way more stuff than my data structures class, then I'm probably going to get more things right on the algorithms section of the test than the data structure of the test. And that's the same thing here with this correlation matrix when you examine sort of how your model is doing in the correlation matrix it outputs. That's why it might be informative. But yeah, this is already running a bit long, so I'm probably going to cap it off here. But I want to say some words since this is the last workshop. So for like what to do next or like what to kind of look at next, the best way that I feel like to learn a lot of this stuff is to do like a project on Rails. What I would recommend basically is to go on like online and think about like something you're interested in. Like, are you interested in image processing? Are you interested in natural language processing? Or maybe these sort of like medical things? And I would just Google like machine learning tutorial, language prediction, right? and just look through, like a lot of people write blogs or tutorials on how to build these, and I would just try and build these. And when you get to like a line of code that you copy paste in that you don't understand, go read the documentation, go look it up, go try and figure out what's going on. I feel like the more you work to like apply these and maybe not spend like all your time maybe watching like a video that explicitly explains what every single line is doing in detail, it's more helpful to sort of do the actual technical do the technical sort of stuff, understand the inputs and the outputs, understand what the model is doing, and then go on your own. And when you come into something you're curious about, read about it and try to understand what it's doing. But if it's not as necessary, don't, I think, try to waste your time to like try and chunk and do every single, like learn every single thing before you actually start making something. I think the really nice thing about machine learning is there's just people that have done so many things with it already that you can easily go online and find a project to start working on, even if you might not have any idea as to what you are doing initially. I definitely think kind of working through stuff and learning along the way is a great way to go about it. But yeah, there's definitely a lot more things to explore that we didn't cover. We didn't cover, for instance, hyperparameter optimization, let's see, we didn't cover a lot of the different optimization or what the different loss functions mean and how to like test and train those. So there's a lot to explore out on your own. And that's what I'd recommend you do, you know, just Google stuff and read documentation and try and figure out what's going on. But yeah, I would definitely go the way of doing fun projects you're interested in and to kind of increase your knowledge that way. Because I mean, the best way to learn is to learn on a method that you're actually going to be able to continually doing and having fun. Like reading a textbook isn't fun. Like nobody likes to like, or I guess, I mean, if you think it's fun, good for you, but like nobody wants to just read dry documentation all day and like say that, oh, I understand what everything does, but I'm just bored out of my mind. So yeah, but I mean, yeah, that concludes our sort of workshop session. And if you have any additional questions, feel free to ask. But yeah, there's no more material past this, I think. Yeah, cool.